Welcome to the second half of Lecture 10. Today's background is a little town called Shibu Onsen in Nagano Prefecture, and it's right on the end of some really nice mountain hikes, including the rather famous monkey onsen, Jigokudani. And one of the nice things about this town is that there's a public foot spa right in the middle of town. So once you've done your day's hiking and you've got sore feet, you can go and give yourself a hot foot soak before you put your boots back on and head to wherever you're going next. In this half of the lecture, I want to finish off Lagrangian mechanics by looking at conservation of momentum and energy, which brings us in the end to something that we call Noether's theorem, which you'll see again later on in mechanics as well. And the argument for conservation of momentum is a little simple, so I'm going to go through it fairly quickly. We're going to do it for completeness, just to pop out what would be an obvious result, but see it from a Lagrangian perspective. And then conservation of energy is more interesting in the Lagrangian approach because you pop out some very useful things that you'll end up using quite a lot in the second half of the course. Okay, so let's deal with conservation of momentum first. A nice feature of an isolated system is that you have translational invariance. So if you imagine having a bunch of particles in here, might have n of them, and they've got positions R1, R2, R3, and so on. What you can do is you can take them through some displacement epsilon, okay? And for today, for the maths later on, I'm going to take them through a displacement in x just to keep things nice and simple, okay? So I'll draw them in x. So this would be epsilon for all of them, same displacement here, to some position R1 plus epsilon, right? R2 plus epsilon, R3 plus epsilon. Okay, now what we do is we think about what changes when we do this, and the things that are important in Lagrangian mechanics are the kinetic energy and the potential energy. Okay, so the potential energy here would become, in any conservative system, it's a function of the position. And in an isolated system where there's no external forces being applied, it can only really come about by the interactions between the actual particles in the system. Okay, so what we're really interested here is the separation between all the particles. What you would have is a potential energy in R1 through to Rn. Okay, so it will be a function of all the separations between all the particles, which will be differences between them all. And when you apply an epsilon to all of them, so you basically take this system and move all of the things to somewhere else, you will get something that's, you know, R1 plus epsilon through to Rn plus epsilon. And again, it's a function of that, so it might be a whole pile of differences or something like that. And it will stay the same, right? If I take particles where the potential energy is dependent on the separation here and I move them all, they keep the same separation, so the potential energy is fixed, okay? So what we can say here is our change in potential energy is equal to 0, okay? Ignoring any external forces, okay? If I had external forces, then the game changes a little bit. The other thing that I have is that if I take a bunch of particles and they're moving, they will have some kinetic energy. And as long as the velocity stays the same, it doesn't matter where they are, they will have the same kinetic energy, right? If I've got two particles here moving at 20 kilometers an hour each, two particles here moving at 20 kilometers an hour each, they will have the same kinetic energy irrespective of that position. So likewise, we can say in here that the change in kinetic energy by some translation of the system is also equal to 0, okay? Now, if we think about a change in the Lagrangian, it can only come about because there's a change in the kinetic potential energy or a change in the kinetic energy. And because both of those things are 0, it's got to be 0, okay? All right. Now, if you think about your change in Lagrangian, and we did this in the first half, you can basically assume it changes because of changes in various variables that it's a function of, right? So your Lagrangian will be a function of x, y, z, x dot, y dot, z dot, and maybe even time. Okay, and we'll ignore time in this case because it doesn't really matter very much in this particular problem. And so we can break it up into that. Now, what we're going to do here, to keep it simple, is assume that we're going to take the translation and just make it in x. So the only coordinates that can change are the x coordinates, right? And we've got n particles, so there would be nx coordinates connected to each one of those particles. So our delta L would be epsilon dl on dx1 plus epsilon dl on dx2 plus all the way through to epsilon dl on dxn, okay? All right, now we know that epsilon is a displacement and it's an infinitesimal displacement, and what that means is that epsilon goes to 0, but it's not equal to 0, okay? And so the only way that delta L can end up being equal to 0 is if delta, actually let's just turn this into a sum. Sum alpha equals 1 to n of dl on dx alpha is equal to 0. Okay, so all I'm really saying here is if I add all of these terms up and that sum is equal to 0, then 0 times epsilon, which can't be 0, will be 0, and so my delta L is 0. Okay, so I'm really just writing delta L equals 0 in terms of something I know about generalized coordinates. Okay, so the one thing that I know is going to hold here is Lagrange's equation. So we can write that real quick. And it's going to be dl on dx alpha is equal to d on dt of dl on dx alpha dot. And we know that this thing here is a momentum, right? It's what we call our generalized momentum, as we described earlier on. So this thing would be d on dt of px alpha. Okay, so it's the x component of the momentum for particle alpha. Okay, and there would be n of these Lagrange's equations for 1 and 2 and 3 all the way through alpha to n. Okay, so there's a whole pile of them. But what we can do is we can take every single term in here and use its corresponding Lagrange equation to make a transformation to this term. Okay, so let's call this equation 1. Our equation 1 will become here sum alpha equals 1 to n d on dt px alpha. And of course, the d on dt can come out the front, so d on dt of sum alpha equals 1 to n of px of alpha. And if we add this up over all those components, this is just d on dt of p of x, which is the total x component of momentum across all the particles, okay? That's got to be equal to 0. And of course, we can integrate both sides here, so p of x is equal to a constant, right? So all we've shown is that when we have an invariance in the system to a displacement or a translation by epsilon in the x direction, that momentum in the x direction is conserved, okay? Fairly simple point, neat little mathematical package. It looks rather simple, and I'm not going to say much more about it except that I'm going to come back to it right at the end of the lecture because I'm going to hook it on to the energy case as something of a broader theorem that exists in physics, okay? All right, so let's switch to energy because energy is actually the more interesting problem here. What we can do is we can write our Lagrangian, and now I'm just going to think in terms of generalized variables, right? So we talked about these a couple of lectures ago. So Q1 through to Qn, and then there's going to be a Q1 dot through to Qn dot and time, okay? And we'll allow time in this particular case because it ultimately turns out to be important to this problem. Okay, there's two ways this can change. And one is that t changes, because if L is a function of t, then L can change. The other is that Qi or Qi dot changes, right? Because the Q's, the positions and the velocities could be a function of time, and then they will change L, right? So there's two ways that this can happen. What we need to do here is get dl on dt. And we're going to do this using the chain rule which we introduced in previous lectures, okay? So it's going to be sum over I, and we're going to deal with the case where the Qi term changes here, okay? So this will be dl on dqi, dqi on dt, plus a contribution from the dot terms changing. So this will be sum over I, dl on dqi dot on dt, plus a term from the time changing, and there's only one of these terms, so it's just going to be dl on dt, okay? And we'll hang on to it for a moment. Later on we'll make it vanish just to keep things simple, but for the moment I'm going to keep it because it's a real thing to have in there, okay? All right, and that's just chain rule. If you're not familiar with it, go back a few lectures where I did it in a lot of detail, exactly how chain rule pops out. We can take this one step further here, so let's just bring this down so I can use the whole line. We can write this as sum over I, dl on dqi. This qi dqi on dt just here is just going to be qi dot. And then sum over I, dl on dqi dot. This term here is just qi double dot, right? So this is qi double dot plus dl on dt. And now the next step in here is that we can use Lagrange's equation and our definition from the generalized momentum to simplify this. And where I'm going here is to set up some notation that you'll use a lot in the second half of the course, okay? So, start with our Lagrange's equation just in here. dl on dqi is going to be d on dt dl on dqi dot, which is just d on dt of p of I, and this is just pi dot, okay, where we know our generalized momentum is p of I is equal to dl on dqi dot, okay? If you're not really familiar with generalized momentum, you should go back and review it, because when you get into the second half of the course, you're just going to lob straight on as though you already know what it is, okay? So make sure you're kind of cool with it. So where we're going to go now is we're going to take our equation 1 up here, and we can write it as d on dt of L is equal to sum over I. This dl on dqi here is just what we get from this equation here, so it's going to be pi dot, right? So we can write this as pi dot qi dot plus sum over I, and then in here this dl on dqi here is just this generalized momentum, right? So this is going to be pi qi double dot just here, plus d partial L on dt, like so, okay, just to carry that last term. All right, the P's and Q's notation, this is probably the first time I've used it in anger. As you go on through mechanics, you use it lots and lots and lots, so make sure you're comfortable with what's going on here, because it's actually kind of important. It's not one of those things that you see once and you never see again. One thing we know is that if we take the derivative d on dt of a product uv, what we get is u dot v plus uv dot, okay? And what you'll notice up here is that we've got some way that we can consider that to be a product rule, okay? So we can take this a step back now. So this is bringing our equation 1 down. It's going to be d on dt of the sum over I. And now what we're going to do is work out on the basis of how this compares with one of these two and how this compares with one of these two, what the uv would be, okay? And so it's going to end up being in here p I q I dot. And so let's just check that this works. What I should get is a dot on the pi and keep the qi dot. So that would give me this term on the left here, pi dot qi dot. And then if I take the dot on the second term here, this time I'm going to get pi qi double dot, and that gives me my pi qi dot double dot up there, okay? And then I'm going to carry this last term on the end down, so this is dl on dt, just here, okay? Fairly simple transition here. Okay, so I've got a general equation here for now, and what I need to do is kind of make the dl on dt go away. And those who did my quantum mechanics course last term will know that we do that when we do uncertainty principle 2, right? We have this extra term on the end. In a lot of cases, it's not very important, so we just make it go away. And so we're going to do that here, okay? And of course, in a case where it's not equal to 0, you can't just ignore this thing, okay? So we have to think about this a little bit more. But in a lot of cases, dl on dt is equal to 0 because L has no explicit time dependence, and the problem sort of solves itself, okay? So if we take this to be the case, then what we've got is basically dl on dt is equal to d on dt of sum over I pi qi dot. Okay, nice simple little expression in here. And of course we can integrate this thing with respect to time. And what we get is L is equal to sum over I pi qi dot, like so. And if we wanted to in here, what we could do is actually make this into a more specific equation, something that looks like sum over I of pi qi dot minus L is equal to 0, okay? And this is something we do, and we do it so much in mechanics that it actually has its own symbol. And this thing that we have just in here is a thing that we call the Hamiltonian H. And anyone who's done a quantum mechanics course will have seen this thing before. Of course, in mechanics, classical so far, we haven't seen it, but later on in the second half of the course, you'll do a whole pile of work on Hamiltonian mechanics where you will use this thing that we've called the Hamiltonian, right? And it basically ends up being the sum of pi qi dot minus L, okay? So it's a useful thing, and in this particular case what we have is that this thing that we call H is equal to 0, okay? So in other words, if L has no explicit time dependence, then H is conserved, okay? All right, we've got H, but at the moment we don't have it connected to anything other than the function that we originally specified it for, right? And we know from quantum mechanics that this Hamiltonian ultimately is the total energy, it's T plus U. But what I want to show here is a proof that it is actually the total energy in classical mechanics without having to define it as such, okay? And what I'm going to have to do here is two things. I'm going to have to rely on my conversion between Cartesian coordinates R and generalized coordinates Q. So if you're not familiar with that, you may want to hunt that back in one of the earlier lectures. The other thing I'm going to do is I'm going to use a mathematical relation that would take me probably about half an hour to derive, and it's just a little mathematical thing. If you have a look in my course notes, I do it, the whole thing, so there's an extra page that basically builds this little relation up, but today I'm just going to use it just to save some time, okay? All right, so what we're going to do here is say that we can have some R of alpha that basically is some R of alpha that's a function of our generalized coordinates Q1 through to Qn, and explicitly not T. And so those of you who remember back to the earlier lecture where I had Mad Pete Evans show up, you'll remember that we had holonomic and natural, and this is what we call natural natural coordinates, okay? And so really what I'm doing here is saying that L has no explicit dependence on T in order to make my Hamiltonian 0, and I'm going to leverage that in terms of my variables not having a dependence on T, i.e. they're natural variables, to connect that to the energy, okay? So ultimately in the end, to make these connections, I kind of rely on time dependencies not coming into how the coordinates behave, and also how the Lagrangian behaves, at least in terms of explicit dependencies, okay? So be careful if you get into extended problems where you're dealing with time dependencies. Okay, so what we're going to do is set out here to prove H equals T plus U. And so the way we do this is we have a kinetic energy, right? And the kinetic energy is going to be a half sum over alpha m alpha r alpha dot squared, right? Okay, and the R here is just the position, same as we've dealt with in any other particular case, and we can write that R as some function of the generalized coordinates of the system. So just to give you one example of this, you might have Cartesian coordinates x and y, and you might actually be interested instead in coordinates that are polar, like r and phi, for example, and your generalized coordinates then would be r and phi, and you can write those in terms of x and y and vice versa, and around you go, okay? And here we're just saying we've got some general expression for that, okay? So what we can do is we can take r and take the derivative with respect to time, because that's what's turning up in this kinetic energy just here, okay? So r alpha dot is basically going to be the sum over I of d r alpha on d qi on d t. Okay, so all I've done here is said that r alpha dot is dr alpha on dt, and because r alpha is a function of a whole pile of generalized coordinates q1, q2, q3 all the way through, I can basically write this as r alpha changing with time because q1 changes with time, because q2 changes with time, because q3 changes with time, and so on. Okay, so I'm basically just essentially using either, well, I'm basically using chain rule here to deal with this thing. Okay. And then, of course, I can take this one step further and write this as dr alpha on dqi of qi dot, right? Okay, nothing more than just application of chain rule, and I don't have a time derivative on the end because I've explicitly said that r doesn't have any dependence on time, right? I'm using natural coordinates. Okay. what I need is actually r dot alpha squared. And so it's going to be basically sum over j of dr alpha on d qj dot. And I know I've changed from I to j. This is deliberate. I'm going to do it. I'm setting myself up for a later part of a problem here. Times the sum over k of dr alpha on dqk qk dot in here. Okay. And if I wanted to, I could call the first one j and the second one j. That would be perfectly fine. I'm just having a j and k so I can keep track of what's coming down below. Okay. This is one of these things you get when you do enough problems. You start to realize when you have to be very careful with your subscripts on sums. Okay. Okay, so now our t here is a triple sum. And it's a triple sum in alpha and j and k now. Okay. So t equals a half sum over alpha m alpha r alpha dot squared is going to become a half sum j and k of a j k q dot j q dot k. Okay, where I bury the sum in alpha like so. Sum over alpha m alpha dr alpha on dqj dr alpha on dqk, and of course it's a vector. Okay, all right. This might not make obvious sense to you just trawling through the lecture, so you may have to sit down and work this step by step for yourselves. Okay, some of these problems, even trying to do them slow like I'm doing them in a lecture is always going to be too fast. You have to slow down and take your own pace to do it. Okay. All right, so we're gonna use something here. We know something about our generalized momentum, P of I, and it's basically that it's equal to dl on dqi dot. And in Lagrangian problems, you've seen enough of them so far. The U, because we're almost always dealing with conservative forces, the potential energy has no dependence on q dots, right? So the only term that's going to carry q dot dependences is t, okay? So already we're putting another assumption into this problem that we're dealing with conservative problems, which, given we're talking about total energy being conserved, makes sense, okay? So this is basically dt on dqi. For conservative forces. Okay, so this is another useful relation just to keep in the back of your heads when you do mechanics. Sometimes it's useful. Okay, so what we can do here is now write dt on dqi dot is going to basically be d on dqi dot of t, and our t is actually given by the expression that we have up above, right? So it's going to be, switch back here, a half sum j and k a j k q j dot q k dot. Okay. All right. I said earlier I'm going to need to use a little mathematical relation, and I don't want to have to prove it so the lecture doesn't take 1,000 hours. So I'm just going to pull this thing down. It basically looks like this. If I've got d on dvi of sum j k for a j k v j v k okay, it will be equal to 2 sum over j a I j v j. Okay, and I can prove this without even needing to know the specifics of the kinetic energy. It basically holds as a result for multiply indexed functions as long as they behave certain commutativity rules. Okay, so if you have a look at my notes, I'll derive this whole thing, but I don't really want to do it here because it's kind of a mathematical tangent that's not very useful. I'm going to use a known result. Okay. What I can do is take this equation 1 up the top and just apply this thing, right? And what it comes out to be is dt on dq I dot is equal to d on dq. Oh, actually, I've already written that line, so let's scratch that one. It's going to be a half times, I can take this piece here and use this piece to get me that one, right? So this is now going to be 2 sum over j a I j, and I'm going to keep the vj's, so this is going to be qj dot, right? So really what I've done is basically just taken a relation that enables me to make the triple sum become a double sum in this problem, with the other sum being buried in the a ij, okay? So of course the 2.5 cancels out, so this thing is basically just sum over j a I j q j dot. All right, now I have a sum that kind of looks like this thing, and it's basically sum over I of p I q I dot. And it's going to be, what am I doing here? I've got p of I here. P of I here is related to d on dt of q of I. Okay, so this is basically sum over I of dt on dqi dot qi dot. It's going to be sum over I sum over j a I j q j dot qi dot, like so. And this thing is going to become sum over I and j of a I j qi dot qj dot. And of course, if we look back up at what our kinetic energy was, our kinetic energy up here is basically a half sum over jk q dot j, sorry, ajk q dot, right? So this thing down here actually turns out to be equal to 2 times t, okay? This section in the middle here is going to look like rather abstract maths, and it is. So you're going to have to work through it on your own to see how it hooks together, right? There's no getting around it. It's not the kind of thing I get you to do in an exam, but it's useful to know how this is done, mostly so that you can convince yourself that this is right, and also, maybe not now, but in later higher physics problems, often you have to use these sorts of approaches with multiple sums to get yourselves out of problems. And so, you know, while I might not ask you to rederive this thing in an exam, this approach might be a problem-solving approach to a problem somewhere, and so knowing how to do it is very useful to do, okay? All right, so I can finish this thing off now. My H, wrong color. My H I defined earlier as sum over I of p I q I dot minus L. And of course, I've just shown that this first part here is 2t, right? So I can write 2t minus L. And of course, I know that L is t minus u. So this will be 2t minus t plus u, which is 2t minus t is t, plus u is the is the sum of the kinetic energy and the potential energy, okay? So I've basically shown, without having to make any assumptions, that this Hamiltonian automatically pops out to be the sum of the kinetic energy and the potential energy. So it's not even like we have to define it like this. You don't have to believe me on anything. We've just mathematically proved that that's the case, starting with nothing other than a Lagrangian, okay? It's a really, really nice little bit of mechanics. And for me, it's probably one of the top 3 or 4 results of my undergrad classical mechanics education, was that you can take this thing called a Lagrangian and out pops the Hamiltonian with the right form, and you use that all over the place in physics, okay? It's kind of nice. And so this leads us to a result in the end here, which is that time independence of L means that total energy is conserved. And of course, that total energy is just a function we call the Hamiltonian. Now, time independence is the same thing as invariance under a translation in time. And one way to see this would almost be as time being a spatial dimension, where you can take the whole system and it looks a particular way at some particular time t0, and then it's time independent. So at least in terms of its formal functional form, it's time independent. It looks the same at t1. And you can imagine that to be a displacement in a time axis, right? So in a similar way to what we dealt with momentum, where we looked at the invariance of the system due to a translation in space, here what we've got is an invariance, or the system staying the same under a translation in time, okay? And that leads us to something kind of nice, which you'll see again in the second half of the course, called Noether's theorem. It's probably for me, probably one of the most significant results in physics, full stop. And when you realize it, you realize both that it's surprising and a very powerful tool. And it basically, the idea here is that every differentiable symmetry of the action of a physical system has a corresponding conservation law. In other words, what we do is tie conservation of various variables to symmetries of the physical system, okay? And when we mean symmetries, what we often mean is invariances under translations to particular variables. So often people think about symmetry as being like a mirror symmetry. The thing on the left is equal to the thing on the right. And so really what that is just, you know, if you do a swap, you get invariance of the system. But you can think of other symmetries in the same way. So translation in space is a symmetry. The system stays the same even though you change the spatial position of it. Time invariance is a symmetry as well. One missing one that we haven't done yet is rotation. So a system looks the same when you rotate it through some angle. Then there's a conservation law tied to that. And what you realize is that there's a conservation law tied to every single one of these symmetries that you have in systems, okay? So you have an invariance in translation in space, and that gives you conservations of momentum. You've got invariance in rotations in space, which gives you conservation of angular momentum, and you have invariance in time that gives you conservation of energy, and then there's other ones you can imagine that give you conservation of mass, conservation of charge, all these other rules. And this is something known as Noether's theorem, and you basically obtain it. We obtained 2 of the parts already today, essentially by starting just with the concept of Lagrangian mechanics and looking at how invariances turn themselves into conservation laws, okay? Probably one of the most significant results in physics, and it's actually a good point, main reason why I've shown a picture on a slide. We spend a lot of time talking about historical men in physics: Einstein, Feynman, Schrödinger, Heisenberg, all these guys floating around. And we never really talk enough about some of the really significant contributions of women to physics, particularly in the past. And there's quite a lot, you know, Curie, Meitner, Guppert-Meyer, Rosalind Franklin, who essentially had Nobel Prize stolen off her, even more recent, Mildred Dresselhaus for carbon nanotubes, all these things. Okay, so it's good to highlight some of these, and in mechanics I finally get to point out one of my favourite theorems in physics, because when I came through as an undergraduate and spotted this, I went, wow, this is actually really cool and really powerful. And it is. It's one thing that you end up using time and again in physics, and often without a name being attached to it anywhere near as much as, you know, things like Heisenberg and Schrödinger and Einstein have their name attached to things. Okay, so it's an interesting place to stop on Lagrangian mechanics. So I think we'll finish there, and in the next lecture we'll start dealing with rotational systems. I'll see you next time.